Welcome back everyone. Today we learn about turning effect of forces. When opening the door rotates about its pivot. This is caused by moments. A moment or torque is the product of force and the perpendicular distance from the line of action of the force to the pivot. The line of action of a force refers to the line along which the force acts. The turning effect of a force is termed as moments or torques that causes an object to turn. Moments are vectors and the directions are either clockwise or anti-clockwise about the pivot. The SI unit for moment is the Newton meter. To calculate moments, the product of the force is multiplied by the perpendicular distance. In this case, the perpendicular distance is the length from the pivot to the line of action of the force as shown here. Using trigonometry, since this is a right triangle, the perpendicular distance can be written as shown with the sine function. Hence, the formula can be rewritten as shown. Let us try it out. Here we have a door. The force exerted on the door is 5 newtons while the perpendicular distance is 10 centimeters. To calculate the moment, we use the formula and substitute the numbers. Do take note where the perpendicular distance is because some students will indicate it wrongly, such as the length of the door. Let's try it out. We have a 10 Newton force being exerted on an L-shaped bar. Determine the moment about the pivot in this scenario. For this scenario, we have to determine the perpendicular distance. Is this a perpendicular distance? No, it is not. The line shown is not perpendicular to the line of action of the force. Hence, this should be the perpendicular distance, which is 1.0 meters. This results in the calculation of the moment to be 10 Newton meters. Now, let us focus on the principle of moments. The principle of moments states that in a balanced beam, the sum of the clockwise moments about the pivot is equal to the sum of the anti-clockwise moments about the same pivot. Here is a diagram to show an example of the principle of moments in action. In conclusion, the sum of clockwise moments needs to be equivalent to the sum of anti-clockwise moments. Let us use an example. Here is the balance shown below. Box 1 has a mass of 500 grams while box 2 has a mass of 1 kilogram. What is D2 if D1 is 50 centimeters? Now, we can do the following. Even though this gives us the following answer of 25 centimeters, this is not the correct method to do it. Why is that so? The question only stated the box's mass and not its weight, hence, mass cannot be substituted because mass is not a force. To solve this, we have to convert the mass into weight. There, that is better. Now, we can substitute the numbers to get an answer of 25 centimeters. Let us talk about simple machines. A simple machine is a device that enables work to be done easily. An example is a lever. The lever uses the principle of moments as shown by the formula here. There are 3 types of levers which are classified based on the position of the load, the fulcrum or pivot, and the effort or force exerted. Although the class of levers is not tested, it would be good to know to understand how these levers use the principle of moments for different purposes. Firstly, let us talk about first-class levers. It is a very familiar setup with the fulcrum or pivot being placed in the middle. Since the distance d effort is larger than that of d load, the force to carry the load will be magnified by the effort. Next, we have second-class levers. In a second-class lever, the load is placed in the middle of the pivot and the effort. Since d effort is larger than d load, the force to carry the load will be magnified by the effort. Lastly, we have third-class levers. Third-class levers have the effort in the middle between the fulcrum and the load. When the effort is larger than the load, a small movement by the effort will generate larger movement to carry the load. Now, let us talk about equilibrium. For an object to be at equilibrium, it needs to have 2 conditions. Firstly, the net force of the object needs to be 0. Hence, it has to be stationary. Next, the net torque applied to the object is 0 Newton meters, meaning it has to be non-rotational. Let us look at an example. Here we have a door. Why is this door at static equilibrium? The door has an overall net force of 0 Newton, and the overall torque about the hinge is 0 Newton meters. Firstly, we need to show that the door is at 0 newtons. Using the vector diagram, we can see that all the forces cancel out each other, resulting in a net force of 0 newtons. Next, we have to show that the net torque of the door is 0 Newton meters. Firstly, for the clockwise moment as shown by the pushing force, we have to find the perpendicular distance. Here, by using trigonometry, since this is a right-angle triangle, we will end up with a perpendicular distance of 0.7 sine 60 degrees. As for the anti-clockwise moment demonstrated by the pulling force, we can use the same method to find the perpendicular distance. This gives us a perpendicular distance of 1.4 sine 60 degrees. By subtracting the moments, this gives a net torque of 0 Newton meters. Let us look at the center of gravity. The center of gravity of the object is the point where the entire body seems to act. For a regular object, the center of gravity is at the center of the object. The example can be as shown. The center of gravity coincides with the point where the object can balance freely. This can be illustrated by the diagram below. For an irregular object, the center of gravity is to be determined by making small holes and freely suspending the object from the various holes. This can be explained in the diagram below. The point where the plumb lines intersect is the position of the center of gravity. Now, this is different from the center of mass. Center of mass is defined as a point at which the whole of the mass of the body, or all the mass of these objects appeared to be concentrated. Although the definitions are not the same, the center of mass and center gravity can be equal if there is a uniform gravitational field passing through the object. Stability is a measure of a body's ability to keep its original position. The stability of a body can be increased by either lowering its center of gravity, or by increasing its base area. There are three types of equilibrium that will be discussed in this topic: stable, unstable, and neutral. In stable equilibrium, the object returns to its original position when displaced slightly. For example, when you displace the prism, there will be a moment that brings the prism back to its original position. In unstable equilibrium, the object does not return to its original position when displaced slightly. For example, when you displace an inverted prism, there will be a moment causing the prism to fall and not return to its original position. Lastly, we have neutral equilibrium, whereby the displacement of the object does not raise or lower the center of gravity of the object. For example, when we displace the cup laid sideways, the center of gravity remains at the same height, but the cup does not go back to its original position. That's all for today. Thank you for the effort to learn with me. Stay tuned for more interesting lessons. See you next time. Bye-bye.